Hello, I'm Yongsu, and I'd like to introduce our work, Escape, Countering Systematic Errors from Machine Blind Spots via Interactive Visual Analysis. Image classification has been a widely used machine learning task in object detection, profiling, or medical imaging. However, recent studies found that systematic errors, which refers to misclassifications over a group of instances that share the similar semantics, can lead to serious consequences with systematic failures. Some examples can include cat images with grass background, misclassified as dogs, or women images wearing eyeglasses or hats misclassified as men. Suppose an example of cats and dogs image classification. When some patterns of cats are missing, such as black cats or cats with grass, which are called machine blind spots, a model will learn spurious associations that are likely to confidently fail over cat images, leading to systematic errors or anomalies. While blind spots have critical consequences, it is challenging for practitioners to capture, make sense, and prevent systematic errors in practice. They are rare and hardly recognizable, and tools are not readily available for them to discover semantic patterns associated with their errors and to validate and mitigate them. However, automatic approaches still suffer from recovering a significant portion of systematic errors with main noises, and there have been no interactive tools to support debugging systematic errors in practice. Our study proposes a human-in-the-loop workflow in leveraging human capability in discovering and detecting interpretable concepts. In the training phase, we investigate whether concepts and certain classes are relatively associated when there is a missing or misleading concepts, and these associations are learned by a classifier. In the test phase, we need to check whether systematic errors are attributed to those concepts, in this case, black cats and cats with grass. Second, we use the approach of concept space to measure and quantify the associations. Images and segments are treated as vectors, which are obtained from an internal layer of deep neural network. This concept vector is a well-known approach, but in this study, we aim to use it toward validating the misclassified images and further propose our statistical method. Based on these two perspectives, we aim to make contributions across workflow, statistical methods, and interactive tool and visualizations. Our system, Escape, is designed to diagnose systematic errors by highlighting misclassifications, especially confidently failed cases called unknown unknowns. Our system supports users to hypothesize the associations between concepts and classes. Then the contrastive analysis view helps users compare different predicted cases. To validate the association, we use our statistical approaches to measure what are the top associated concepts over the training set and how concepts are actually influential to misclassify the images in the test set. The mitigation method tries to debias vectors by projecting them to the orthogonal direction of the concept. Let me illustrate a scenario as a case study where a data scientist Mark, who inspects the image classification of cats and dogs, aims at inspecting false predictions. Once he opened the system, he noticed in the performance chart that misclassifications with a high confidence took up a non-negligible portion. When you looked at the confusion matrix, the degree of misclassifications was indicated with the size of bigger outer circle and the degree of unknowns as the size of inner circles, which are more than falsely predicted dogs. When he moved on to instance space, he noticed all instances are represented as circles. Confidence histograms allowed him to see the distribution of confidence score over predictions, with misclassifications colored as light or darker red bars. By adjusting the sliders, he chose instances over 0.85 of confidence score to exclusively examine unknowns. While he did a further exploration, he found a group of cat images with person concepts that were falsely predicted with high confidence, and a group of misclassified dog images with cage. When he adjusted filters to select both true and false instances, he identified a set of images with grass that are densely grouped with each other. When selecting those instances, They appeared in contrast to view, which is a flowchart-like layout that shows how image patterns in four confusion cases are different from each other. Each confusion case, for example, false positive, which is a misclassified cats, are represented as an arrow from true class to predicted class, and connected to the panel where images are displayed. In this case, contrastive view showed that instances with grass concept falls into two cases that are both predicted as dogs. This suggested that there could be a bias of this grass concept towards dog class. Now Jane tried to hypothesize and validate if grass concept was learned to be a pattern of dog class. The system allowed users to define concepts, which are defined with a set of segments that are semantically coherent. First, she clicked Add Concept button, and the system immediately turned to concept mining view. She selected two cases where many grass concepts appeared, and clicked the segmentation button. Once the segmentation is over, segments appeared in segment view with rectangle-shaped icons. She selected it by clicking the region of interest, then clicked the Add button. Once a concept was added, it appeared in the concept list. In the system, concept association plot allows users to examine the concepts regarding how concepts are associated with misclassifications. In the plot, the 7 identified concepts were represented as a vertically aligned pair of two circles, each representing false positives as upper circle and false negative as lower circle. These three circle pairs were plotted in the two-dimensional scatter plot, whose x-axis indicates how the concept is biased towards either cat class or dog class, and the y-axis indicates how the concept is influential towards either misclassified cats for the top half or misclassified dogs for the bottom half of y-axis. He wanted to closely examine the cage concept by clicking it. He found that the concept detailed view showed what are the detailed images that were most associated in the training and test set. It was interesting that the top associated images in the training set were mostly cats but included diverse objects such as cage, wall, leash, or floor rocks. It indicated that these various objects with stripe or grid-like pattern may have been learned as a similar pattern. After the investigation, Mark decided that grass concept is the most noticeable in spurious concept association, so she clicked the debias button to see how he can remove the unwanted concept associations. The debias view showed how spurious associations can be mitigated as more number of grass-associated instances are debiased. He selected 200 instances to be debiased and checked that debiasing method can mitigate 56% of spurious associations. To evaluate our study, we conducted a set of quantitative and qualitative evaluations. In our quantitative experiments, the combined concept association was proved to better capture the associations across different datasets than existing concept association methods. And the method for debiasing spurious associations was also proved to be effective to mitigate errors when the classifier was retrained with debiased vectors. Additional case studies confirm the spurious associations and systematic errors in other datasets. The second case study showcased how a multi-class classification with Pascal bulk dataset can be addressed. We also investigated another dataset called Cellavay and found that the classifier systematically failed over some woman images who don't smile or wear eyeglasses or hats. User study allowed us to investigate human behavior in concept discovery. Overall, users were able to find diverse patterns over 26 unique types of concepts. But we found that there is a trade-off between precision and recall. Humans are better at precisely capturing spurious associations, but suffer from low recall. This brings the need of human-AI collaboration. Leveraging both automated methods and human capability for discovering subspaces into the workflow might be helpful. In this work, we investigated the problem of systematic errors. We proposed Escape, a visual analysis tool for countering errors from spurious concept associations that promote the workflow of human-AI collaboration. We showed that humans are capable of capturing the spurious associations more precisely than automatic techniques, and it shed light on the role of the humans and the need of exploring better ways to make collaborations between humans and automatic techniques.